So how do we figure that out? To figure out the bias and variance, we need to figure out what is our answer random variable, right? So let's first figure out the mean. So my answer random variable, let's say P, is equal to the mean, which is 1 over n times the summation of a indicator random variable, right? I goes from 1 to n. A indicator random variable of xi square plus yi square greater than 1.99. So that's the probability I compute, which is by itself a random variable, because this let me just call this big X and big Y, because this big Xi and big Yi, both of them are random variables, and they are also independent random variables for different i's. Let's pause here a little bit and think about, in computing this P, what is my random space? Here we see a true example of a huge random space. We have a random space that is 2 million dimensional, right? So we are drawing, actually, the computer is drawing in a fraction of a second 2 million random variables. And here, basically, we are picking one point from this extremely large space of all possible things that can happen, right? The computer can draw a very different set of 2 million random variables. And then we are computing a function of this, a function in this 2 million dimensional space. So P is actually can be thought of as a 2 million dimensional function, because P depends on every single xi and every single yi. Right? Okay, so now let's figure out the statistical property of this P. So first of all, what is the mean of P? And mathematically we use the capital E to denote the expectation or the mean of that random variable. So the expectation has a very nice property that the expectation is linear. Right? Do we all remember what linear means? A linear operator means if the operand is scaled by 2, the result is also scaled by 2, right? Right, and if you have 2 operands that are added together, the result is also added together. So here, because P is equal to that thing, we know first of all that if P is scaled by 1 over n, I can move that 1 over n out of that expectation, and then we have expectation of a summation. Right? And then another opportunity to apply linearity. The expectation of a summation is just equal to the summation of expectations. So expectation of this indicator random variable. Now, computing the expectation of a 2 million dimensional problem has been simplified using the linearity property into computing the expectation just over 2 dimensions, right? Because now a single expectation only involves 2 random numbers, xi and yi. So, what is that expectation? What is the expectation of a indicator random variable? Yes, the expectation of an indicator random variable of if an event happens or not is simply the probability that this event has happened, right? So that can be simplified to summation of the probability that xi squared plus yi squared is greater than 1.99. All right, and that probability, because each xi for different i's are identically distributed, they are all uniform 0, 1, right? And each yi for different i's are also identically distributed. So that probability is the same for different i's, which means this summation and this 1 over n can just disappear, and what I get is the probability for any of the x plus any of the y's greater than 1.99. That is actually exactly the probability we wanted to compute in the beginning. Which means that through our Monte Carlo method, we get a random variable, yes. We get a random answer, yes. But the expectation of that random answer is actually the true answer we are looking for. So a Monte Carlo method with this property is called unbiased, which simply means the bias is equal to 0. Right? That's a very sought after property of Monte Carlo methods. In this case, it's almost trivial to get a unbiased Monte Carlo algorithm. But in many cases, it's a little bit more complicated. For example, if you have an algorithm to estimate not the probability of something, but the standard deviation of a random variable, right? Then it's a little bit more complicated to get a Monte Carlo method that gives you unbiased estimators. All right, and sometimes it's even impossible to get an unbiased estimator. For example, if you want to figure out the maximum of a random variable, nobody knows how to construct an unbiased estimator, right? The best thing you can do is to look over your samples and choose the maximum number that occurred in your sample, and that for sure is biased, right? It's biased towards the smaller direction, because the maximum of the random variable, the maximum that can possibly happen, of course, is greater or equal to what has happened in your finite samples. So Monte Carlo method is not always unbiased, but the Monte Carlo method here for estimating the probability of an event easily can be unbiased. Now we have answered one of the questions is, we know the answer of a Monte Carlo method is a random variable, it's a Gaussian random variable. It can be characterized by mean and standard deviation. The mean in this case is exactly the same as the answer we are looking for, so it's unbiased. The remaining question is how much variation there is from one execution of the same algorithm from the next. All right. Well, what is the variance?